Yeah, so welcome. So it's my great pleasure to introduce today's speaker, Andy MacKenzie from the Max Planck Institute in Dresden. And like it's not only him, he actually brought quite a crowd, as I can see. And so welcome everyone. So maybe for those of you who are here the first time, we do this bi-weekly. And if you want to receive the announcements, just drop me a line and I can include you in the mailing list. So the subject, or say, is usually everything that's hydrodynamics in electronic systems. Yeah, so it's my great pleasure to introduce Andy MacKenzie, and he will talk today about new developments in his group, in his experimental group. And yeah, without taking anything further from you, the floor is yours. Thanks for sharing this with us.
Okay, thanks very much, Lars. So the actual history of this invitation is that I'm co-editor of a review article journal, and I was tapping Lars to write a review on electron hydrodynamics for our journal, so he tapped me to give this talk. And I explained to him that I would give him an unconventional title because the search, we are maybe, I'm going to give you a case study essentially of all the complications that can come on trip you up when you're doing a search, at least for viscous effects in hydrodynamics. So long list of collaborators. I always get a nightmare that I've missed somebody out. I hope not. I'll be referring to work individually as I go along, so I hope you'll see there where they come from and what they've contributed. And what I'm going to do is assume quite a lot of prior knowledge for everybody, since this is a seminar on electron hydrodynamics. But I will just say a few words about shear viscosity and its role in electron hydrodynamic transport. And then I'll talk about the channel flow experiments that we have done on ultra-pure delafoscites and a series of lessons that we've learned over the years. Now, I myself am a pretty stubborn guy, so I don't tend to listen much to lessons learned by other people. I tend to pay more attention to lessons learned by me. But so I'll only talk about our work, but I do actually think that some of the things that I'll talk about today are of relevance, not just to people doing other experiments on electron hydrodynamics, but to theorists trying to look at experiments and decide whether they believe the assertions made in the papers are credible or not. So to preface my my conclusion, look away now if you want, if you're interested in electron viscosity, because contrary to what I thought 5 years ago, I think there's not such great evidence that the non-local transport that we see in the delafossites is dominated by viscous effects. But it's dominated by something else that was, to me, completely unexpected and pretty interesting, which is that that we have ballistics going on, but of a non-standard kind. And we've coined the term directional ballistics for that. So in part 3, I'll show you some examples of directional ballistics experiments and the effect that these directional issues have on magnetotransport. And then in the very last experimental results slide of the whole talk, I'll mention some very nice electrodynamics measurements that are going on in Doug Bond's group in UBC on our samples. Then I'll draw some conclusions, which I hope will be obvious by the end. So the brief primer to the role of shear viscosity in flow experiments comes where you start thinking about flow of any fluid through an empty channel, and we'll do it in 2 dimensions because that's the dimension we'll be thinking about electrons in. And if you were able to look inside the channel and measure the velocity profile, you would find that the fluid was moving faster in the middle of the channel than it is at the edges. And that's because you've applied some pressure gradient to send your fluid moving. It has momentum and it needs to lose that momentum to have flow resistance. And the only way that ideal fluid can transfer momentum to the outside world is at the edges of the channel. by interacting with the edges of the channel. So that means that the flow resistance is going to be related to a transverse coupling, say, of an element of the fluid in the middle of the fluid to the edges. How well does an element of fluid here know about these edges where the fluid is relaxing its momentum? And the strength of that coupling is the origin of the quantity, the shear viscosity, sometimes quoted as a kinematic viscosity, where you divide out the mass density of the fluid. So microscopically, a little bit of consideration of that is then surprising to people with solid state physics, or the physics of solids as their preconceptions, because microscopically, imagine that this fluid is a fluid made up of particles or simple molecules, for simplicity. There'll be a mean free path for scattering of those fluid particles. Microscopically, they'll be scattering off each other all the time as the fluid is flowing. But those scattering events don't lead to flow resistance because they result in the transfer of momentum from one particle in the fluid to another one. So the overall momentum of the fluid isn't relaxed by any of these blue processes. It's only relaxed when you get a momentum relaxing collision of an element of the fluid with the boundaries, as stated before. And that then leads to this non-intuitive result that, or motivates this, to me, non-intuitive result, that the longer the mean free path inside of the atoms or the particles in the fluid is, the more efficiently they can find the boundaries and do momentum relaxing scattering. So this applies to any form of transverse coupling. So the viscosity of this fluid is proportional to the momentum conserving mean free path. And because the viscosity is proportional to the flow resistance, we end up with a flow resistance which is proportional to the mean free path in the fluid, not inversely proportional to it. But that's very non-intuitive for people who work on solids most of their life. But that's because this is an unusual mean free path. It's a mean free path for scattering events which conserve the overall momentum of the fluid. So I'm going to call it script L sub MC for that, momentum conserving. Now, these considerations also go over to quantum particulate fluids. And the most famous of these is arguably liquid helium-3. And this graph here tells you an important lesson that backs up this rationale that I just developed.
Can I interrupt? There seems to be a problem. Like I'm still stuck at the fluid flow through an empty 2D channel slide.
Whoa.
And apparently some people only see a black screen.
Well, this isn't good, is it? Okay.
Well,
right.
Should we maybe?
So what I'll try doing.
To start over the.
Yeah, what I'll try doing is going into presenter mode. I'll stop the share. I will restart the share on the presenter mode. Are you now seeing still I'm on the fluid flow through an empty 2D channel slide.
That's what I'm seeing.
Right now, as I change this, do you see the changes? Have you seen more text?
Yes, I do.
Do you see the new channel, new slide?
Yes. How about everybody else? I see thumbs up. Okay, seems to be working. Great.
Okay, so I don't know, you're recording the talk. Do you want me to repeat everything I was saying? Or do you still remember and you can relate it to these drawings?
I think it's fine.
Okay, so now we're on liquid helium-3. Okay, so the famous result from liquid helium-3 is that the measured viscosity, which you can measure with various torsional type experiments, the measured viscosity is diverging as T to the -2 roughly, because you're in a Fermi liquid. So phase space protection is cutting out your ability to scatter. So the momentum conserving mean free path is getting longer as the temperature goes down, and therefore the viscosity is increasing. And again, that is a strange thing at first sight. It's still non-intuitive to me because of the background I come from. You know, in a sense, the better the fluid, so the lower the scattering, the less scattering that's going on within the fluid, the more viscous it becomes. And this is a very real effect because at least some of the data I'm going to be showing you today were taken in dilution refrigerators. And this increase in viscosity of helium-3 as you get to low temperatures is the ultimate limit on the temperature of operation of a dilution fridge. By the time you get to 10 millikelvin, helium-3 has similar viscosity to motor oil at room temperature. And you're trying to pass it through very narrow capillaries. And at some point, you just hit a limit where you don't have the pumping power to do that anymore. So it's entirely real. So all of that was for classical and then neutral quantum fluids. But there was a famous prediction back in the early 1960s, just before I was born, that similar things might in principle be observable in ultra pure metals. And what Gurdjieff pointed out was that the resistance of an ultra pure metal might look like this. So here you have the flow resistance going down, and he was talking about wires. So he was thinking of some sort of spatial restriction as well. So here you have the resistivity going down, which as the temperature decreases, which never happens with the viscosity in helium-3. And that's because you have here momentum relaxing electron phonon scattering, which isn't present in helium-3. Then you have a crossover region as the phonon scattering dies out. And then he predicted that shear viscosity effects might take over because of momentum conserving processes such as electron-electron scattering, but also in very special circumstances, some kind of electron phonon scattering could allow the viscosity to take over, have the resistivity rising before it then flattened off as the width of the wire became the smallest length scale in the problem. So this predicted increase of the resistivity of a metal or a metallic wire as the temperature goes down is now known as the Gurdjieff effect. And one of the goals of many experiments on electron hydrodynamics is to observe it. Now, it's a wonderful paper. It's a great idea, but I have to love my theory colleagues because it's very easy to put these statements in the title of your theory paper, like impurity-free conductor. That really doesn't happen very often. And in fact, the difficulty with looking for electron hydrodynamics is that the channel isn't empty. It contains the lattice in which the electrons are flowing. And that lattice will have many forms of imperfection, which I'm denoting here by the red dots. So that means that in the bulk of this, of your electron channel, you have momentum relaxing conditions, an internal momentum relaxation, which is happening inside the pipe, if you like, not just at its boundaries. And that internal momentum relaxation must always be very carefully considered when we're thinking of real electrons in real solids. And in the vast majority of solids, just the defect scattering, just the impurity scattering is so high that you have no chance of ever seeing a viscous effect. So bearing that in mind and knowing a little bit about the interest in electron hydrodynamics, I thought that there might be some relevance to studying doing these kind of experiments in special materials called the delafossite metals. This is just the name. Delafosse was the French crystallographer who I think discovered the crystal structure of the delafoscites, but they are oxides of this form. So they have a noble metal, a transition metal, and O2. But empirically, the really remarkable thing about them is that they have extremely low resistivity, so extremely high conductivity. That for the theorists in the audience, that room temperature resistivity is about the same as that of copper, but the carrier density in the delafossites is about 1/3 of that of copper. So they actually have the most mobile metal electrons at room temperature of any proper metal with a full metallic density of electrons. I don't want to go into too many material details, but just take it from me that they're also quasi two-dimensional. The resistance perpendicular to the conducting planes is about 1,000 times the resistance in the conducting planes. And it's the in-plane resistance I'm showing here. So as well as a very low resistivity at room temperature, they have a very large resistance ratio, at least in good crystals. In other words, the resistance drops by a factor of a few hundred between room temperature and low temperatures. That means that you get low temperature resistivities of a few nano-ohm centimeters, or which a simple analysis tells you corresponds to in-plane mean free paths of tens of microns. And a mean free path of tens of microns, if you think in semiconductor terms, that's about the mean free path that was required in order to see the fractional quantum Hall effect with high resolution in two-dimensional electron gases. So that's an extremely long mean free path. And the other thing that I knew, again, which is something that we analyzed in detail in this 2012 paper, I don't have time to talk to you about it in much more detail, how we deduced it. But there's evidence that below 50 Kelvin or so, there may be a phenomenon called phonon drag going on, where instead of the phonons remaining in equilibrium with zero net momentum as you put on an electric field and give the electrons momentum, instead of that, you drag the phonons so that the phonon fluid gets momentum at the same time as the electron fluid getting momentum. And that's potentially important for hydrodynamics, because then your electron phonon collisions will be themselves momentum conserving for the overall electron fluid rather than momentum relaxing. So phonons in general are the enemy of hydrodynamics, but dragged phonons are a friend of hydrodynamics. And so we had that very much in mind when we thought we would try some experiments. The other thing that we had in mind was that the delafoscites are beautifully, wonderfully simple materials. Only one band crosses the Fermi level, and the Fermi surfaces that result are simple single Fermi surface sheets with hexagonal facetting. But it turns out that if you look at the magnitude of the Fermi velocity, it's pretty much K independent around these Fermi surfaces. Therefore, we believed when we started the experiments that we could analyze our experiments pretty much in terms of expressions derived for circular Fermi surfaces. Now, one of the messages I'm going to give you is that that was not a correct assumption to have made, and it's going to be part of the meat of today's talk. So please, again, bear that in mind. So the other thing that you need to do if you want to look for hydrodynamics is to make devices, because you need to make flow channels whose minimum dimension, usually their width in 2 dimensions. These flow channels need to have a width which is short enough to becoming at least comparable to some of the other length scales in the problem, the microscopic scattering lengths. So we can grow these crystals 10 to 20 microns thick. And with modern focused ion beam techniques, it's possible for us to sculpt them into almost any shape we want. And for the first simple experiments we were doing, we wanted that just to be, if you like, a Gurji wire, a 2-dimensional flow channel where each of our 2-dimensional planes were just conducting in parallel, but along a channel whose width we were going to restrict. And we set out to do the simplest conceptual experiment possible, which was to measure the channel, make the device, measure the channel resistivity, narrow the device by a factor of 2, remeasure the resistivity, and so on, as we successively changed the width of the channel from 60 microns to about 700 nanometers. And the basic deductive path we followed is worth discussing because it's the same as that followed in most general terms in almost every experimental search for electron hydrodynamics, which is that you perform a transport measurement, you fit it to a hydrodynamic theory. I wouldn't be saying this if you didn't then get a pretty good fit to a hydrodynamic theory. So you declare success and bask in the glory. Now, there are known to be already, even before what I'm going to tell you today, there are known to be problems with assumptions from that procedure. One of the big assumptions that affects many experiments are assumptions about boundary conditions. Because the boundary scattering is vital, you really have to know how your boundaries do scatter. And that's a kind of hidden problem with many of the ways that you try and make these restricted channels. That one actually doesn't affect us too badly because the focused ion beam gives a thin damage layer right at the surface. And you can even microscopically look at what you've done, and you've more or less put in random disorder. So using no slip boundary conditions to analyze our experiments is, and I think still is, a reasonable assumption. However, other implicit assumptions go into most people's hydrodynamic theories and certainly did into ours, and I'll explain that as we go along. More specifically, what we did was some people will just use the Navier-Stokes equations directly to make a hydrodynamic prediction and compare it to their data. Slightly better is to take a kinetic theory that maps onto the Navier-Stokes equations, but gives you more degrees of freedom, because in Navier-Stokes, you're just assuming that momentum relaxing scattering is irrelevant, usually, and that you're just thinking about momentum conserving scattering. Kinetic theory allow you to tune the ratio of the momentum conserving and momentum relaxing schemes. And in fact, in some beautiful work in semiconductors in the 1990s, Molenkamp's group and with de Jong had made some observations that they thought could be the Gaugy effect. So they coded the earliest kinetic theory that I'm aware of that would allow you to do this kind of fitting. So we simply took their theory, re-derived it to check that we knew what we were doing, and recoded it and used it. And when we did that, here's what we got. We had the following data points, which are the data we got for the flow resistance of the channels as we changed the width. And we plotted them in a dimensionless way, where you normalize the resistivity of the resistance of the channel to the resistance expected at infinite width. And you normalize the x-axis. In the x-axis, you took the width, the inverse width that you'd made of your channel, but you normalize that to the known momentum relaxing mean free path. And if you do things in that way, and you use the theory to think of only the momentum relaxing processes, so you don't imagine any viscous contribution, you get a prediction which has no further free parameters when you're using these units, which is like the blue curve. And that blue curve comes out of the de Jong and Molenkamp theory, but it had been discussed and predicted for ballistic devices in semiconductor physics even earlier than that. So you see blue curve, not good fit to data, red curve, much better fit. And when we got the red curve from that particular hydrodynamic kinetic theory by saying we weren't in the absolute hydrodynamic limit, but it predicted that we had some process giving us a momentum conserving mean free path, which was about 1/10 of the momentum relaxing mean free path. So we got good agreement when we looked at the from a kind of long range over a wide range of this parameter on the x-axis, but there was more information in there as well. So if we zoom in to what we saw down at lower values of this ordinate, one of the signatures of a viscous contribution is curvature here. So a purely viscous response would have been quadratic. Down at low values of LMR upon W, a purely ballistic response would have been linear. And what we saw was neither linear nor quadratic, but it had curvature on the way to quadratic. And that matched intuitively with getting parameters out from the fit, which made us look not purely ballistic, but with an additional viscous contribution adapting the results. And a number that I'd like you to bear in mind is that the parameters that came out of the fitting we were doing, for us, the momentum conserving mean free path really was just a fit parameter, and it came out to be about 2 microns at 3 Kelvin. So we'll come back to that number in a few minutes. Now, the reason that we need to think one reason we need to think very carefully about that number is that anybody who's worked on semiconductors or graphene makes the microscopic assumption that electron-electron scattering from the different electrons in the fluid is the source of momentum conserving scattering. Because the idea is that when one electron scatters from another, just like a helium atom scattering from a helium atom, they exchange momentum, but they don't relax the momentum of the overall electron fluid. Now, you can argue about exactly the way that you want to calculate the strength of electron-electron scattering, but for the purposes of just basic estimates of how it's going to look in different systems, these expressions here, adapted from a famous paper by Giuliani and Quinn, I think are adequate. What they tell you is the following story. If you are wanting to do a hydrodynamic experiment at 10 Kelvin, then you're fine to do that in a device of micron scales in a 2-dimensional electron gas. Even in graphene, and this is known by the people who work on graphene, you're not so great. The electron-electron mean free path is pretty long, 80 microns at 10 Kelvin, at the densities that people are typically doing graphene experiments. But it drops such that it becomes reasonable for doing hydrodynamic searches between, say, 50 and 100 Kelvin. So it's no accident that many of the hydrodynamic claims in graphene are being made on data taken in those ranges of temperature. In palladium cobaltate, though, we have a Fermi temperature which is metallic, 27,000 degrees. That means that our electron-electron mean free path at 10 Kelvin is of order a millimeter, not 2 microns. So there's, unless some special enhancement of electron-electron scattering resulted from having this hexagonal Fermi surface, it just doesn't look hopeful. It looks like electron-electron scattering couldn't possibly be the microscopic source of that momentum conserving length that we fitted out. And it looked much more likely or much more hopeful, the remaining hope was that this phonon drag was going to be important, and that the scattering between the electrons and the dragged phonons would end up being capable of giving us the momentum conserving length that our experiments suggested. So that was kind of where we were at the end of the 2016 experiments. But we were carrying on, and we were trying to add magnetic field and do magnetohydrodynamics has a different meaning, but let's call it magnetoelectron hydrodynamics. And by 2018, we were extremely enthusiastic about what we were getting. So here's a slide from a talk that I hunted out that I gave at the March meeting in 2018. And we could do magnetohydro experiments now up at 100 Kelvin, say, in palladium cobaltate. We could take an adapted version of Navier-Stokes in which you were taking momentum relaxing scattering as well as momentum conserving scattering into account. We could make assumptions which weren't too egregious on the scale of assumptions made in the field of analysis of experimental data for hydrodynamics, and we could match what we were getting really very well. So we also got extremely good agreement between analyses of this form and experiments that we were doing on the Hall effect. And so, yeah, we were very excited. We were excited to the extent that we wrote a manuscript that was more or less ready for a triumphant submission. And we thought to ourselves, though, there's only one thing that we can't do on the basis of this approach, even with the momentum relaxing processes in it. We can't check whether physics that was actually morally ballistic rather than morally viscous and hydrodynamic could possibly give us the same thing. Now, we were at 100 Kelvin, So we thought there was no chance, but we did know we were looking at pretty small effects at 100 Kelvin. So Thomas Scafidi implemented a full kinetic theory that where fields could be applied in our particular circumstances, which was very computationally intensive at the time. And just before we were sending our damn paper, his magnetokinetic model showed us that we had no discriminatory power on the basis of these observations between a ballistic and a hydrodynamic interpretation. And over those early years of the rebirth of electron hydro, I think many people were saying the same thing, that the margins or the difference between ballistic physics and hydrodynamic physics was not as great as we'd intuitively assumed previously. But in the spirit of giving these lessons that I've learned, I think the key lesson that's learned here is that if you are using Navier-Stokes-based theory as your start point to analyze data and make a hydrodynamic claim, you need to realize that you've made a big assumption there. You've assumed hydrodynamics, predicted something, seen it, and therefore assumed that that was the unique explanation of your data. And that's sometimes okay, but as we learned in this project, it can sometimes be very misleading. So in fact, that paper metaphorically is sitting gathering dust on shelves. We never submitted it anywhere. And the experiments and a lot of analysis of them went instead into Nabanila Nandi's PhD thesis, which then expands on some of the lessons that we learned there. So at the same time, as we were very excited about that particular form of magnetohydrodynamics, we were also trying complementary experiments on something called transverse electron focusing, which is a well-known experiment from the physics of very pure metals and the physics of semiconductors. And we had both a ballistic and a hydrodynamic motivation for doing these experiments, or a search for hydrodynamics motivation. But what is the experiment? So what you do is you have a current source and you make a very narrow contact. So you approximate it to a point contact or a Charvin contact, as it's known in the literature. And you study the voltage that you get between a grounded current contact here, big, thick, big one, and a second voltage point contact, which you put somewhere along a line from where you had your current injection contact. And if you're doing this in a purely ballistic sample at zero applied field, then you are just going to do billiard balls with, in our case, rough boundary conditions, so non-specular scattering at boundaries. And in the purely ballistic limit, the way that the current will find its way from source to sink will be through this range of collisions all the way through the solid, through your device. But now if you apply a magnetic field out of the plane, those injected carriers will start to make cyclotron orbits. And as the field gets big enough, the way they'll be getting eventually to the current sink is by cyclotron motion, non-specular scattering, another section of cyclotron motion. You may sample your voltage contact as part of your trajectory, but eventually that electron will make its way out to the current sink. Now, if you then increase your field such that you have the cyclotron diameter is equal to the length spacing between your current injection and voltage probe contact, without going into too much detail, you certainly expect something to happen there. And it turns out there is a magnetic focusing effect where all of a sudden, a lot of electrons start landing at where you had one of your voltage contacts, and that changes the voltage that you're seeing between your voltage probe and your ground. If you then have a very good sample and you increase the field by a factor of 2, you'll see a harmonic. So you will see electrons that have done a double skip as they've been on their way to your voltage contact. And so we can, as I said earlier, sculpt basically any kind of sample we want. So Maya Bachmann made really a very direct copy of that cartoon. And we had current injection here. And we would always put, she made many devices, but we would have a series of voltage probes so that we could sequentially study the signal we got at the different voltage probes. And one of the things we discovered, first of all, was that you get really spectacular verification of the fact that you have this huge mean free path that you believed that you had from bulk transport measurements. So here we have the injection point and the voltage probe point separated by 35 microns, a huge distance. And yet we're able to observe, depending on how optimistic you are, either 9 or 10 harmonics of the focusing peaks. So whatever else that tells you, it tells you that you have these really large mean free paths and you've got a direct mesoscopic caliper on them. But the other kind of device that Maya was making was motivated by experiments we'd seen in graphene and discussions we'd had with colleagues in the graphene community. She made another focusing device where she made the separation between the probe contacts much smaller, about a micron, and she made the probe contacts themselves very small, about 250 nanometers. When she looked in that device, she saw these beautiful, it's a little complicated, apologies for that, but she saw again this hierarchy of beautiful focusing peaks. They're separated by much more magnetic field now because the contacts are more closely spaced. And so you need a higher field to get that kind of cyclotron radius. But what was really exciting us was that if you forget all of the focusing stuff and you just look near zero field, we were seeing a easily resolvable negative voltage at zero applied field. And we saw that if you have very good eyes, you would see that the size of that voltage went down the further we moved the probe contact from the current injection contact. And that was of relevance to us because we were all very well aware of predictions, very nice predictions from Levitov and Falkovich, and very nice experiments on graphene, where you predicted and then observed this kind of negative voltage in a geometry like this as a consequence of electronic viscosity, right? And so at the same time, when we first saw that negative signal, we had our original flow experiments that I told you about at length. We had the magneto experiments that were seeming to confirm a hydrodynamic interpretation. And then we had this negative voltage that again seemed to confirm the viscous interpretation. So we were pretty happy all around. However, very much like the way that we theoretically did, maybe unwisely, just that final check, here we did just that final check experimentally, because the device that we'd seen the original negative voltage in was quite small, 20 by 10 microns. And there was always the residual worry that, again, a negative voltage might be hydrodynamic, but it also, particularly in a small device, could be conceivably a ballistic effect itself, some form of back reflection or something like that. So Maya then did the absolutely direct experiment again. She made a much bigger device and realized that in the much bigger device, she didn't see the negative voltage at zero field anymore. Right? We got the orange thing of the positive voltage. So was that because the two devices were different? Well, you can do something fabulously direct with the fib. She just turned this device into the small device again. And when we made the device small again, we were able to get the negative voltage to come back. So that was pretty worrying in terms of the intuitive hydrodynamic interpretation. And we don't have absolute proof, but I would say our negative voltage was probably also a ballistic effect. So the lesson learned there is that even phenomena that you think of at first as really intuitive smoking guns for electron hydrodynamics or for viscous electrons, they're not always what they at first seem to be. So Maya's focusing experiments proved to be highly influential in our research in another way as well. if you were looking carefully at the peaks that I was encouraging you to ignore previously, now I encourage you to look at the peaks. And in the devices she was making, we had a real structure to our peaks, some kind of peak shoulder or incipient double peak that was not seen in any of the previous semiconductor or graphene work. And we were extremely puzzled about this for a long time. For a long time, we were trying to think of ingenious ways that that structure could itself somehow be a viscous effect. But then Maya began to really worry that maybe the ballistics that we were seeing were very much more strongly influenced by the faceting of our Fermi surface than we thought they were. So again, beautifully, she just did a really direct experimental test of this. She fabricated another focusing device where everything was identical along that edge and along that edge, except that because she changed the edges by 90 degrees, she had a different effective Fermi surface orientation for the way that for the distribution of how the injected electrons were going to be. And sure enough, when she changed from this direction with the double peak to the other direction with the different injection distribution, she saw that the peak structure and the structure in the peaks completely went away. So we then realized that this must mean that the ballistic consequences of our faceted Fermi surface were actually far more profound and relevant to observation than we'd expected them to be. So we went away with that in mind to go one step better. We went to David Goldhaber-Gordon's group. They have these beautiful ballistic Monte Carlo simulations that they'd used for their own focusing experiments on graphene. We gave them a tight binding parameterization of our Fermi surface, and they repeated the Monte Carlo studies for injection in both directions of electrons, which would come out with a distribution corresponding to this hexagonal Fermi surface of ours. And as an experimentalist, I really, really always enjoy and re-enjoy showing theorists a graph where the theory is noisier than the experiment, right? But that's what Monte Carlo will do for you. But when we take away my enjoyment, what you see is that the theory, the analysis that these Monte Carlo experiments came up with captured the structure of what we were seeing really very well. And it also accounted for the lack of structure when we injected with the different orientation. So those Monte Carlo simulations did an uncannily good job of reproducing what we were seeing. And that simulation contained no viscous contribution. That's purely ballistic. There's no hydrodynamics in there. So again, that combined with the other, well, I don't want to call them calamities, but the other reversals of intuition made us realize that we had to be very careful about any assumptions we'd made in the past that ignored the importance of that Fermi surface faceting. And in the original paper that I told you about, the channel research, where we deduced a viscous contribution, we had ignored it twice because we had not, in those very early days, deliberately oriented our channels in any particular direction relative to the Fermi surface. And we also we'd done our theory on the basis of a circular Fermi surface. And we believed that both of those were not a worry. But now when you realize that the ballistics that you're seeing are very strongly affected by Fermi surface orientation, you would say that experimentally, the circumstantial evidence that we were building, that we were coming up with against a unique hydrodynamic interpretation was building and building. So I was already becoming a pretty suspicious person. And in some senses, the final nail in the coffin, as far as I'm concerned personally, came from theory, not experiment, because all of our hope was that the momentum conserving scattering in our dragged electron phonon soup was what was giving us that mean free path of 2 microns. And both Levchenko and Shmali and Huang and Lucas went away and did careful analyses of the predicted temperature dependence of the viscosity, and therefore the temperature dependence of the flow regime, of the flow resistance that you would expect if that was the source of the momentum conserving scattering. And they come up with, at these very low temperatures where we'd done our experiments, the prediction is kind of unambiguous and very strong. It says you should have a T to the -5 resistivity at low temperatures. And we observe nothing like that. We observe only a very weakly temperature dependent effect. So I at least have to conclude that all of our non-local transport, including what we observed in those original flow experiments, was the result of ballistics, not viscosity. There may be a tiny viscous contribution, but it may well come from additional effects to do with the way you scatter from impurities. It's not coming from electron phonon soup. And so if we want to continue with hydrodynamic language, our experiments are much more in the Knudsen regime than the Parsoy regime. And so I no longer believe the strength of conclusion that we made in our 2016 paper. So there's another big lesson. If one wants to play the electron dragged phonon card, which many people are playing these days in interpreting other experiments, it seems to me that the strongly temperature dependent viscosity is a very clear prediction of that scenario. And to me, if you're not observing that strong rise of viscosity and flow resistance as you lower the temperature, I don't think you've got a very convincing claim that you're seeing viscous effects. Personal opinion. So now I'd like to move away from all of that, destructive language to much more constructive language, and say that I certainly don't believe that because we're in if you like, a hexagonal symmetry Knudsen regime, that what we're seeing is uninteresting. Actually, I really quite like what we're seeing. So now I'm going to give you some examples of that. And I see I have about 15 minutes of the allotted time left. So the first of these is to go away and just directly demonstrate directional ballistics. So we could infer it from the focusing experiment, but Maya, in her PhD, and now we've finally written up and have an archive paper about it, she just went and did the most direct experiment you can think of. You take your hypothesis, you take a single crystal, and you sculpt from the same crystal a single channel of electron flow where the electrons are flowing for similar lengths, but at different angles relative to the underlying Fermi surface. And in this language, the orange channel here, the electrons are being injected in there, and every time they scatter internally in there, they're being re-emitted with directions that mean that almost none of them are being re-emitted along the channel direction. They're always being re-emitted at an angle which makes them scatter with the channel boundaries pretty quickly. Whereas by the time you go to the blue channel, the opposite is happening because you have a substantial proportion of your electrons, about half of them along the flow direction, are being injected and then re-emitted from scattering events along your channel. So if this directional ballistics is correct, you have a rather pronounced prediction of a rather pronounced hard and easy direction for transport in these wires, as long as the wires are being made substantially narrower than the momentum relaxing ballistic mean free path. And this is, in a rather textbook way, exactly what you see. I haven't stressed it, but the hexagonal symmetry or triangular lattice of these materials means that in bulk, if you're in the ohmic regime, the transport has to be isotropic. So if we go up to 100 Kelvin, our mean free path is short enough at 100 Kelvin that we are essentially in the ohmic regime, and we see no difference of resistance for flow along our hard or easy directions. As the temperature goes down and the mean free path goes up, that begins to change. And in a 2.5 micron channel, wide channel, we see over a factor of 2 difference between hard direction and easy direction transport. And this is kind of remarkable because these channels are not fully ballistic in the purest sense of the word, because their length is much, much longer. Their length is nearly 10 ballistic mean free paths, right? So what we're seeing here is this strong directional effect in a quasi-ballistic situation where we know there are occasional scattering events going along in the bulk of our channel, but still the very strong directional effects persist. So that, I would say, is, yeah, that's an example of, if you want glamorous language, hexagonal Knudsen physics in electrons. You can then do something which is even more analytically sophisticated and, in my opinion, more cool, but a little bit more complex. This is now the thesis work of Philippa McGuinness, and the device work and the experiments were shared between her and Elena Zhakina. So what they did was to go back and make one of the kind of classic device structures that people had studied in mesoscopic physics before. They decided to make squares where they injected current into the corners of the square. And you expect to see a number of interesting things when you do that in the ballistic regime, but the circular symmetry of the Fermi surfaces of the original experiments meant that you expected whatever you saw to have the full fourfold symmetry of the device. In the delafoscites, that's no longer the case, because the combination of the hexagonal Fermi surface and the square symmetry of the device can lead to, does lead to a lowering of the symmetry below the full fourfold symmetry of the device, but you maintain some of the fourfold operations. And the ones that you maintain depend on 2 different orientations, which Philippa and Elena call the enhanced and the diminished orientation. So the way the experiments progressed was our usual. We start out by making a big device, study its properties, and then sequentially make it smaller while preserving the device symmetry. And the kind of thing they observe is the following. So in the enhanced orientation, it turns out that the symmetry involved in a perfect device would say that if you study what are called bend resistances, either with current going in the bend 1 orientation or bend 2 orientation or the bend 1 orientation, you should see the same thing. And within reasonable resolution, they do see the same from the 2 bends. But here's another example in purely ballistic physics of where you see a negative apparent resistivity. And you see that because, let's look at the bend 1 orientation. You're sending your current in this way. Yeah, look, let's imagine another convention. We're sending it in along contact 1, eventually sourcing it along contact 2, but you have a decent probability of making a ballistic trajectory straight across the sample to, if you like, pile up electrons in one of your voltage contacts. That distorts the voltage you're seeing from what you might expect, and it's the physics that leads to the negative resistance. And this is well known and well studied from the 1990s, because here the symmetries don't give you a big difference from what you would have seen with a circular Fermi surface. However, if you do the same experiment with a new device, which has been cut in the so-called diminished orientation, which has rotated the Fermi surface by, I always get mixed up between 30 and 15 degrees. I'm going to say 30 degrees and then they'll yell at me afterwards, right? But you rotate the Fermi surface into the diminished orientation, and there you see this huge anisotropy. So for one of the bends, you see the negative resistance coming in, but for the other bend, you see a large positive resistance. So in the end, you see this massive anisotropy of your response, even though that anisotropy disappears again. In both cases, the ballistic effects disappear when you get up to 100 Kelvin, and your device doesn't care about its shape at all. It's just an ohmic device. So you can then extend that, and they did extend it to magnetoresistance. And there's a lot of detail in here. You get funny effects, which are to do with electron focusing as you apply a large magnetic field. But at least, although you've got competition, complications of that focusing, nothing is happening to fry your intuition yet, because you're measuring what you think of as fundamentally a magnetoresistance, and it may do strange things, but at least does them in a way where they're even in the applied magnetic field. If you go to the if you go to the enhanced orientation, and you look, instead of the magnetoresistive contacts, you look at the Hall contacts, again, you see some strange effects which are ballistic. You don't just see the linear ohmic response, but what you're seeing turns out to be odd in field, and you feel warm and happy, and that's all okay. If you do it in the diminished orientation, you not only get a shock, but we got a shock to the extent that the first thought was this was a dud device, because you're trying to do a Hall effect measurement and you're seeing a very structured response, and that very structured response is totally asymmetric in field. It's neither even nor odd, and it just looks, if you like, intuitively crazy. So a lot of head scratching went on there, and we went away and learned a lot of physics that we'd never had cause to learn before. We wondered whether, can it be that you're breaking time reversal, but that seems completely crazy. And indeed it is. Because what you're actually seeing is a beautiful example in a real system of this result, a famous result that Buttiger came up with in the 1980s, where he realized that the Onsager relations that you use in ohmic transport, a lot of them, all bets are off when you go to non-local transport, but one of them survives. And this is a generalized Onsager relation, which Buttiger showed should be obeyed in any system, no matter what transport regime you're in. And it gives you a prescription for a change of contacts and a simultaneous change of field direction, which would lead to a symmetry which simply has to be obeyed. So Philip and Elena went away and did this experiment. First of all, they changed the contact direction. They plotted it in their usual field axes. But then you flip the field axes and you see that the non-intuitive data completely beautifully lies exactly on top of each other. So what they saw there was a lowered symmetry situation where the only symmetry you could find left in the system was this final generalized Buttiger-Onsager symmetry. And Philippa, in her thesis and in a paper that we'll hopefully be posting on the archive soon, used Landau-Buttiger analysis to do a full symmetry analysis of what they're observing, and showed that everything in these complex experiments can be explained by Landau-Buttiger formalism, conservation of current, and conservation of time reversal symmetry. The other cute thing is that because we're a metal here and we have a very short Fermi vector, we can do a quantum transport calculation, or at least estimate, with 12,000 quantum channels instead of just a few quantum channels. And we can get the general magnitude of the effects that we're seeing in real units, in voltage per current, or if you like, in resistance. We can get that correct within factors of a few by doing the full Landau-Buttiger estimate. So we thoroughly enjoyed that. I think it's not viscous hydrodynamics, but it's cool physics from which I've learned a lot, mainly being taught it by my students, and I like that very much. So this is my last experimental slide. Started a few minutes late, so I will end within the hour. These same ideas of the importance of Fermi surface orientation, we're now seeing in a great collaboration with Doug Bond's group at UBC. I mean, the data are really from them. They took our crystals and they cut devices for microwave experiments in both orientations, where you've varied the orientation of the hexagon you're studying relative to the orientation of the underlying Fermi surface. And what they see with a really nice broadband bolometric technique, where they can study all frequencies up to 20 gigahertz in the same sample, what they see is a measured an easily resolvable difference in the frequency dependence of the microwave surface resistance that they get from the samples in the two orientations. And the key to understanding that is very similar to before. They're obviously studying the response of the electrons within the skin depth of these crystals they're studying. And in one of these two orientations, you have something that you never have had before, which is a substantial fraction of your electrons being injected or moving or possessing Fermi velocities, which are parallel to the surface being studied. And that is, Graham is doing, along with advice from some of the other theorists in the collaboration, Graham is has done a very, very nice model where he can match the key features of the data, at least to a decent accuracy. And that confirms that this special thing of having a substantial subpopulation of electrons moving parallel with Fermi velocities parallel to the surface is the key to understanding these results. So I don't know what we're going to end up calling this because, you know, we had the skin effect, the anomalous skin effect. This might be, in the language of Hall effect, the unconventional anomalous skin effect. I don't know what name Doug and the colleagues are going to coin for it. Doug was telling me last night that, again, a paper will be coming onto the archive about this in the not too distant future. So that is my time up. So I'll stop talking there. Those are my conclusions. I'll just let you read them. I hope it's obvious from what I've said. And I'll be very happy to take your questions. Thanks for listening.
Thank you, Andy. Impeccable timing. So there must be questions. So if you have questions, please speak up.
I thought I was going to get lively abuse at this.
No question yet. So let me maybe start with one. So you mentioned in one of the last slides these 12,000 channels that match it.
Yeah.
So is this like a number? Like it doesn't sound like a fitting parameter to me. Is that like a realistic number for the system? Or
yeah, I should have been. It was too quick. Yes, it happens that they have usually worked with 7 micron wide contacts. And in the normal way that you relate your contact width to your inverse to your Fermi vector, to your inverse Fermi wavelength, you come up with this very strange number. And that is because our Fermi wave vector is about 100 times bigger than the Fermi wave vector in any semiconductor system at their densities.
Okay. Okay, thanks.
So yeah, but really, normally when people are doing those experiments, they're thinking, 10 channels would be a lot.
Yeah, because I mean, 12,000 is, yeah, it's quite a number.
No, so what I got a huge kick out of was realizing that you make a decent fist. You have to make assumptions about transmission coefficients, but with assumptions that I at least claim are reasonably benign, you make a decent fist at explaining that kind of difference between the maximum negative and maximum positive resistance within an order of magnitude.
I see a hand, Maxime. Please speak up.
Thank you very much. It was a very interesting talk. I just wanted to follow the logic better. So originally, you were kind of surprised that basically ballistic explanation, or disappointed, I would say, that ballistic explanation works better than or more justified than just viscous hydrodynamics. But could you anticipate this ahead by just making estimates of the relevant length scales? Why can you just say that? Let's say you. So you see, I just want to understand why it took you by surprise, in a sense that if you just compute or estimate the length scales, momentum conserving versus momentum relaxing, length scales, etc., you could know this maybe ahead of time.
You could certainly make that accusation, but there were things that we didn't know in 2015. And probably we were excited and optimistic, right? But at least for me, looking in the literature, it wasn't so easy to know exactly what your electron phonon length scale was going to be when you were dragging those phonons, right? So I was hoping that, and you know, we were looking for a scattering length of 2 microns, which is still a fairly long length. So it didn't seem inconceivable to me that the scattering in a soup of electrons and dragged phonons could give you a length like that, right? And I also, now, if I'd read Gurgis' papers more carefully, I would have been more educated than I was on temperature dependencies. But really, until I saw the re-derivation in some senses of the predicted temperature dependence for a process like that, I was clinging on to residual hope, right? But it's the, so you know, the absolute length scale, I think, is, you know, it involves cross sections of things. It's harder to estimate than the temperature dependence. And the temperature dependence, I didn't know until Alex and Jörg showed me the results of their calculation in 2019.
Yeah.
So that would be my excuse. Now, we also had a slight excuse for electron-electron scattering, and that's actually been looked at in detail as well now by Andy Lucas. So we were using the hexagonality of the Fermi surface as an excuse where we wanted it to, but it wasn't done deliberately. It was done in hope, right? What we thought was, is it so clear that you really understand the magnitude of electron-electron scattering, even in the presence of Pauli blocking, when you have a section of Fermi surface that looks quasi one-dimensional? So and again, that wasn't totally clear to us. I mean, and so, you know, we put in the paper that we just didn't know. And Andy Lucas then went away with Caleb Cook, and they confirmed actually that one-dimensionality does lead, all other things being equal, to an enhancement of scattering, right? But they also showed that the enhancement isn't nearly enough to save your skin if you've got a Fermi temperature of 30,000 degrees.
I see. So just to make sure I follow you, your hope was based on 2 things, basically, that you have a phonon drag and that you had an evidence for this before.
Yes, we have evidence of phonon drag.
Right. So that was, yeah. Yeah. But then this probably kind of complicated because there are umklapp processes within the phonon systems, and there is a whole theory that had to be developed.
Correct.
Right. And yeah, so for this, okay, no, I see the rationale.
Yeah, and at sufficiently low temperatures, you don't need to worry about electron phonon umklapp, because your phonons are really, you know, the way you tell that you've got phonon drag is that your measured resistivity looks activated, because you don't see resistivity from phonons until you bridge the umklapp gap.
I see.
So we knew from our resistivity that the standard gross resistivity of a single crystal was not seeing any of the normal electron phonon processes. So all of those were going to be the friend of hydrodynamics, but we didn't know how many they were, right? And now we do know, and it doesn't match.
Thank you very much. It's clear.
Are there further questions? Yeah, I see a hand. Igor.
Hi. This is Igor Shevkoy. I was just wondering about this following thing. With the lessons learned about this system, about the ballistic regime, is there any hope that in this material that could be realized the hydrodynamic regime at all?
The best hope is the finite temperature stuff, right? So to go up to, you know, you maybe you end up with a window, you know, at 70, 80 Kelvin again. But that's really extremely hard to determine, because the umklapp gap for the phonons is about 160 degrees. And that means that by 70 Kelvin, there's a lot of umklapp phonon scattering going on as well. So the very best you're going to be able to get to will be you know, that really sets a limit. The momentum relaxing mean free path is already down a few microns or a couple of microns, say 70 Kelvin. I need to look again. Therefore, you would need a momentum conserving mean free path much less than that. And it's just going to be, again, a balance. You know, that would need, again, to be a detailed electron phonon calculation, I think. But, you know, you might, in principle, be able to find something, right? And you'd be repeating these kind of experiments and reanalyzing them, or reanalyzing our existing data set, which is very large. But I think that what you would come up with would always be a small viscous correction to, by then, quasi-ohmic behavior. And given, you know, I don't think that electron hydrodynamics doesn't exist. I think there's pretty good evidence that it exists in graphene and in these semiconductors. So if I were a theorist working on hydrodynamics, my main message would be, I would be looking at low density systems to get definitive results.
Okay. Thanks.
Okay, thanks. Are there more questions? Well, I don't see any. It's also already getting late. So let me thank Andy again for the very nice talk, very honest talk. Yeah, and yeah. So yeah, I wish everybody a good evening, good night, or wherever you are. Maybe nice lunch. Okay.
Yeah.
Yeah. See you around next time. Bye.
Thanks a lot. Right. Bye.
Bye. So.